It can be challenging to visualize a three-dimensional vector on a two-dimensional screen or page. However, it is important to try to visualize vectors in three dimensions, such as vector A shown here in blue to the right. The sum of its rectangular components defines vector A. So similarly to what we saw in two dimensions, now we have three dimensions, so now we have a z direction as well. So this vector equation is stating that vector A equals vector AX plus vector AY plus vector AZ, where each of these is one of the component vectors, one of its rectangular components. Notice in this diagram here that an additional vector, A prime right here, has been established in the xy plane. This vector is an intermediate vector known as the prime vector or shadow vector of vector A. So we do notate it as a prime with a prime symbol there, a little tick mark, single quotation mark. And we can also call it the shadow vector because if you imagine a three-dimensional space and say this vector A is being represented by a stick or something like that or a rod, and we have, say, a source of light right up here shining directly downward, then that rod or that stick would cast a shadow, which is being represented by the prime or shadow vector. So the prime or shadow vector is located in the xy plane. And notice that the prime vector, A prime, can be obtained by adding the AX vector, the X component, to the AY vector, the Y component. So a couple of relationships here that are important. These vector equations are important to realize that they do hold true. Vector A prime equals vector AX plus vector AY, and furthermore, vector A equals vector A prime plus vector AZ. By establishing the unit vectors I hat, j hat, and k hat to define the positive x, positive y, and positive z directions, respectively, we can express vector A in Cartesian vector notation as the following. Vector A equals scalar ax times the unit vector I hat, plus scalar ay times the unit vector j hat, plus scalar az times the unit vector k hat. And as you might recall, the reason I'm saying hat when I say ijk, I hat, j hat, k hat, is because when handwriting these unit vectors, we need to include the caret or hat symbol above each one of them. That's the upside down V or caret symbol, Shift 6 on your keyboard. So this is a general Cartesian vector expression of any three-dimensional vector such as vector A. The magnitude of vector A can be calculated knowing the magnitudes of its components. So if we do know the magnitudes, AX, AY, and AZ, we can apply the Pythagorean theorem in three dimensions, which is what this formula is, where the magnitude, scalar magnitude of A, which is not in bold because this is just a scalar magnitude, that magnitude of A equals the square root of the sum of the squares of the components. Okay, that's square root AX squared plus AY squared plus AZ squared. And as we just mentioned, this useful formula is known as the Pythagorean theorem, now in three dimensions. The direction of three-dimensional vector A is not as straightforward as specifying the direction of a two-dimensional vector because now we're in a three-dimensional space. Here we define the direction of vector A using coordinate direction angles known as alpha, beta, and gamma. These are Greek letters, alpha, beta, and gamma, written as you see here. These are the lowercase versions of alpha, beta, and gamma. So these angles, coordinate direction angles alpha, beta, and gamma, are defined as the angles between the vector A and the positive x, y, and z axes respectively, and each angle is between 0 and 180 degrees. So this can be difficult to visualize in three dimensions, but we have to make sure and get this correct. So what we do here is imagine vector A, just like it's already shown. If we locate the vector A or position it such that its tail is at the origin of the xyz coordinate space, then alpha is the angle between the vector A and the positive x-axis, this angle here. Beta is the angle between the vector A and the positive y-axis, and gamma is the angle between the vector A and the positive z-axis. So you do have to imagine for each one of these. Imagine, let's say for alpha, let's take that as an example. Imagine this line, the line of action of vector A, and the x-axis, those two lines form a plane. So you have to think of this in the context of that plane. Alpha would be the angle between those two lines within that plane. And similar thing for beta with respect to the y-axis, and gamma with respect to the z-axis.